Okay, so we talked about the series circuit last time. So here's the stuff I want for reference. I have a 12-volt battery, and I connect a 1 ohm and a 2 ohm to it in turn. Those are my simple circuits. I always want to go back to those as a baseline because I'm going to use the same battery and the same two resistors to connect in various ways. I did the series before, and next I'll do a parallel. And so I want for reference what is the current that each of them draws, what is the power dissipated by each one. We find that the less action happening at the big resistors, it allows less current, dissipates less power. And then here's our master equations, Ohm's law, of course, our power law, and if you need to compute it from first principles, what the resistance of something is, although oftentimes that's given. So let me review for you. This is all stuff that I had on the board last time. I'm just going to fill in a new column. So in a series circuit, when two things are in a row, so this, I guess I can draw the circuit we did last time. We had a 12 volt, we put the 1 ohm and the 2 ohm in a row. So this is a river with no forks, so whatever the current is going to be the same through each resistor. So the total current courses through one, then the other. Current's always the same through each resistor. I don't mean the same in every single series circuit no matter what it is. What I mean is that whatever the current is, it's the same through each resistor. But the voltage drop is not. We found that we had to split up the voltage drop so that the larger resistor had the larger voltage drop. You give a bigger energy reward for going through a bigger obstruction in the chain. I'll come back to that. I want to make a kind of a conceptual point about that. The resistor addition rule is you just add the resistors. You add the individual resistors to get the total or equivalent resistance. If it's not already obvious, that means that the total resistance or equivalent resistance is going to be greater than any individual one in the chain. Again, you may wonder why I would bother writing down such an obvious statement, but it's going to be because we compare it against parallel. And then finally, if you had n identical resistors of all of resistance R, you just multiply how many you have. So that would be your shortcut if you were so lucky as to have a bunch of identical resistors. We also found that the large resistance dissipated more power. So I've circled here the big resistor that's like the bottleneck. All the action is happening on the big resistors. They have them. If something is not the same, then it's bigger for the bigger resistor. So the bigger resistor, if you have a bunch of resistors in a row that you have to go through, the biggest one is the biggest show in town. It's the bottleneck. It's got the most voltage drop. It's got the most power dissipated. Okay. So over here, if you have a series of resistors in a row like this, there's going to be more power and more voltage drop on the big one. So this right here is a concept that you really need to internalize conceptually. If you're waiting on the math to provide this result, then you're going to be very sad when you get some kind of conceptual problems. Let me give you an example. So let me just extricate those two resistors from that. And I'm going to assume that there is some kind of constant voltage drop across the whole thing, probably by a battery. But what we learned is that how much voltage drop is taken by each is going to be related to how much resistance each one has. So we already know that the larger resistance has larger voltage drop. Okay? So just to make this a little bit more tangible, let's just go ahead and put some numbers on it, okay? So let's say, for instance, that the constant voltage across this whole thing is 10 volts. So as an example, maybe the voltage drop would be 1 volt and 9 volts, okay? So it has to add to 10, but apparently one resistor is 9 times the other because it hogs 90% of the voltage drop, okay? So that's basically the concept we just talked about. But one of the things you should also be comfortable with is not just looking at which resistor is bigger and which one's smaller, but changing the resistances, okay? So here's something you could do. Let me label these. I'll call these R1 and R2. So let's say you exaggerated the situation even more. Let's say I increased R2. If I increased R2, that would make voltage 2 even bigger and take away from voltage 1. Okay? So if the ratio of resistances changes, then the ratio of how much voltage drop is taken by either one. So I guess I can try to draw that. It would look like this. R1 is the same, but now apparently this is even bigger. So now maybe this will be, I don't know, let's just make up some numbers. So 0.5 and 9.5. Notice I'm taking care to make sure that they still add up to the same value, but now the ratio of how much is taken by one versus the other has changed, okay? So if you have a bunch of resistors in a chain and you take the biggest one that already hogs the most voltage drop and you make that even bigger, it'll hog even more of that voltage drop. Now that's hopefully fairly intuitive, but you can work this the other way. Let's say I make R1 larger, I increase it. I'm not saying I make it bigger than R2, but I'm just saying I make it larger than it was before. Well, that's going to have the same idea. Now that's going to increase its voltage drop at the expense of the other one. So anytime a resistor gets bigger, it's going to take a little more voltage drop than the other one, and the other one's going to decrease. So for instance, maybe it looks like this. I make R1 a little bigger, but this one is still the same. So I'm always going to refer back to the original situation. I guess I should write that. Okay? All right? Now, R1 is still the smaller one. So it still gets less voltage drop than this one. What I'm saying is that if I increase this a little bit, it's going to take a little more. So maybe this is like, now this is like 1.5 volts, and this is like 8.5 volts. Okay? So if you make one bigger, it'll take more voltage drop than it had before, and the other one will have less than before. Okay? Does that make sense? Now you could do something like this, right? You could have that, I don't know, let's take R1, which is already the smaller one, and decrease it further. Well, if you decrease it further, that's going to mean that it's less voltage and the other one has more. Okay? So notice that whatever you do to the resistance of one of the resistors, that's how the voltage drop of that one goes, and the other one has to compensate. So for instance, again, if we're referring back to the original situation, if you take the smaller resistor and you make it even smaller, well then, now you're going to split it very, very extremely. Let's say that this might be even like I don't know, I guess I could, let me put it the same as the second case. So now they might split like that. The difference, of course, between these two cases here is that here it changed from the very top line. Here it's because I made the bigger one bigger, and here it's because I made the smaller one smaller, right? So in both cases, if you start messing around with the voltage drop or with the ratio of resistances, you start messing around with the ratio of how much voltage drop they each take. Oftentimes, a bunch of resistors in series is called a voltage divider, because they literally will divvy up the voltage between them, the journey from beginning to end. And if you start messing around with what the ratio of resistances is, you start messing around with the ratio of voltage drops they each take. Okay? In fact, you can even see it right here. If I1 equals I2, which of course they do because they're in series, you can plug in V1 over R1 is V2 over R2. Which means that these ratios are going to hold no matter what. So if you start messing with the ratio of resistances, you'll start messing around with the ratio of the voltage drops they each take. Okay? So this is, if you understand this about series circuits, you are in a very good place for a lot of different types of conceptual questions. And I would especially urge you to note this second one. This second one can get confusing, and here's why. Sorry, that's the third one, I guess, the second modification. So here, make sure you understand that there's a difference between R1 still being smaller one versus R1 being increased from its previous value. So we're taking R1, the smaller resistor, we're making it bigger. It's not as big as this still, but we have increased the value. So if we increase the value, we have increased the value of that voltage drop from its previous value, but it's still the smaller one. Okay? So I've increased V1 at the expense of V2, but V1 is still smaller than V2. Okay? So whichever resistance is bigger will take more of the voltage drop, but if you make the resistors closer to each other, then the voltage division is not going to be as extreme either. Okay? So make sure you understand this right here. If I increase one resistance, I will increase the voltage drop, but if it's a smaller resistance, then overall the voltage drop is still smaller than the other one. So it's basically, do you understand, if a quantity can be smaller than another one while still increasing. Okay? I'm going to refer back to this several times later today. It's really important for, even in the context of larger circuits, to understand. When you start messing around with the ratio of resistances, you start messing around with how much the ratio of voltage drop is taken. Are there any questions on that? Okay, so we're ready now for the parallel circuit. So the parallel circuit is going to be the exact same battery, 12 volts, EMF. And I'm going to put the two resistors in a parallel configuration. Now here they literally look parallel, but that's not what is necessary for them to be electrically parallel, as I will show you. This is R1, which is 1 ohm. This is R2, which is 2 ohms. And we're going to ask all the same questions about this. What's the current through each one? So what are I1 and I2? What are the voltage drops across each one? What's the power dissipated across, with each one? And how do we look at this circuit as an equivalent circuit? So if we were to replace both resistors with a single resistor, what would be the equivalent amount? So basically, how much does this entire circuit resist overall? So there's going to be a total current drawn. We can apply Ohm's law to the equivalent circuit. So the total current that will flow through the circuit is based on the battery we connected to and the equivalent resistance of the whole thing. Because remember, the circuit senses how much resistance is in the way, and the current will flow accordingly. All right? So let me go ahead and start with the voltage side. So I'm going to circle my equipotentials. It's always a good thing. So here's my higher voltage equipotential. I guess I'll call that A. It's the higher voltage terminal of the battery and any contiguous piece of conductor that's connected to it. So that's the highest voltage plateau that I'm going to start falling from. And then I'll circle my lowest voltage equipotential. And I'll call that B. And that's it. There are only two plateaus in this whole circuit. There's a higher voltage and a lower voltage. And the difference now is that you have two different options to go between them. If you want to get from A to B, and positive charges do, that's what they do, is go to lower voltage, then you can go through either resistor 1 or resistor 2. There would never be any single charge that would go through both of those, because there would be no reason for that. If you want to get from A to B, and you chose to go through resistor 1, why would you then go from B back to A? That's where you didn't want to be, so why are you going back there? So there's nothing that will flow down here and up here. What you will have is charges flowing. Some will flow through this way. I'll call that I1. Some will flow through this way. I'll call that I2. So if we go back over to our chart, we understand what parallel circuits are is when the voltage drop is the same across each element. What you are offering is multiple options to get between the exact same two voltage regions. So the voltage drop between these is the same, and in fact, that is set by the battery here. It's 12 volts. So we can say V1 is the same as V2, which is the same as the EMF. It's 12 volts. Okay, so we're done with that. That is the motivation for charges to go from A to B, is to get to 12 volts lower. Okay, but if the charges are equally motivated to go from A to B by either path, the 12 volt drop is the same. And we might draw one of our voltage waterfalls. It looks like this. So you can think of the battery as a pump. And then now it's like two waterfalls side by side. You can drop through that entire voltage through two different options. This is our equipotential A. This is our equipotential B. And we have two different options to do that. So notice how that contrasts with the series circuit where it's one waterfall after another. These are two waterfalls side by side. Now if the motivation is the same, the resistances in each path are not the same. So that means that the same amount of charge is not going to choose to go through each option. We're going to find that more goes through the easy way. Makes sense, right? So we go ahead and we figure that out just using Ohm's law. I1 is V1 over R1, and I2 will be V2 over R2. And we can go ahead and calculate that. There's a 12 volt reward for going across that one, but only 1 ohm of resistance, 1 ohm of obstruction, so 12 amps go through there. There's 12 volts of motivation to go through the other resistor, but it's a 2 ohm obstruction, so only 6 amps goes through there. This is where the idiom path of least resistance comes from, because more charge will go through the path of least resistance. The smaller, less resistance path offers, the more charge will choose to go that way. So if we add that to our chart here, the current is not the same. And in this one, I guess I'll say that if the resistance is larger, then less will go that way. So I'll talk about it always. I like to peg it to the large resistors. So the large resistances get less current. It's the hard way. More go through the easy way. What's happened to these large resistances now? They are no longer the must-do, right? If you have a series chain, you got to go through everything, which means you got to pay the most attention to the big things in your way. Well, now the big resistance is no longer the bottleneck; it's the sideshow. Okay? Why would you go through here when you could go through here? So now I'm going to circle the big resistances again, but I'm going to refer to them as the sideshow. That is not where the main action is. The main action is in the path of least resistance. All right. So here's my analogy, right? If you have, you're trying to get home on your commute, let's say, you have multiple routes. So this path of least resistance is like the highway, okay? So highway is built to take a lot of cars easily. It's a wide tube, large cross-sectional area, 5-6 lanes. Okay, very similar to a small resistor. It's very wide. Your other option might be local roads, right? So local roads have stop signs, traffic lights, things like that. It's not as easy. You might question why anybody would bother to go through here, right? Well, as you know, if everybody tries to take the highway, it's not the most efficient way to process the flow. it makes sense for somebody to still take local roads, just not everybody. If you were driving somewhere and you saw everyone was taking the highway and there's tumbleweeds on the local roads, you might take the local road. So it still makes sense for some charges to go through the hard way, just fewer of them, okay? Does that make sense? Okay, so notice the kind of cross thing here. It's reversed here, which one's the same and which one's not. So series, current's the same, voltage is not, and parallel, vice versa. Okay? So that's usually the easy thing to remember. Just remember that out of current and voltage, one of them is the same and the other one's not, and it's reversed for the other type of circuit. All right, so let's go ahead and further explore. We've got the voltage and current already all set. And at this point, we could certainly get the power. I guess let's knock that out. So the power, again, I have 3 different forms to choose from. And I suggested this one for series, not because the other ones are wrong, but it's really hard to mess up if you use that one, because the current's the same for everybody, right? Well, this one, I will suggest for the same rationale to use the last one, the one that has voltage, because that's harder to mess up for parallel, because everybody has the same voltage. Okay? So I guess let's go ahead and do it. So P1 is going to be V1 squared over R1. P2 is V2 squared over R2. And there's nothing that could plug in wrong because the voltage is, of course, 12 volts for everybody. 12 volts over 1 ohm and 12 volts squared over 2 ohms. We get 144 watts and 72 watts. So what we find is that there is actually more power dissipated in the small resistance. Okay? Notice here that since V is fixed in this equation, we have that P is now proportional to 1 over R. So since V is the same for everybody, that means that the power dissipated is inversely proportional to R. If R increases, then the power is less. I'm going to add that over here. Again, it's a lot easier in this chart that I'm building to always refer to what's going on with the large resistances. Notice that the large resistances used to be where the most power is dissipated. Now it's where the least power is dissipated. And I like to think of it for exactly the same reason. The large resistances are the sideshow now. The charges have better options. They will go, more will go through the easy way. They don't all have to go through everything. And so the more they go through the easy way, it leaves that the large resistances are kind of marginalized. They get less voltage, or they get less current, and they get less power. If you want to go back to the original formula and explain this, why is this? P equals IV. Well, this is the same for both, which means that the same energy is lost per charge. So when a given electron traverses either one of these resistors, it loses the same amount of energy. So it's the same energy loss per charge. That's what voltage is here. But the difference, of course, is that the charges do not split evenly. There are far more going through the easy way. So if there are more charges per time through the small resistor, then there will be more total power for the small resistor. Okay? So that's the way to think about why the power dissipated is actually larger for a smaller resistor. So small resistor, larger power. That's where all the action is in a parallel circuit. Or not all of it, but most of it, right? Okay. So the final order of business we have, first we have to think of it, how are we going to think of this as an equivalent circuit? And then let me hook it up and we'll check to make sure that the demo agrees with some of our calculations. So first things first, we have that the current through this fork of the river was 12 amps and over here was 6 amps. Well, those ultimately, of course, came from a common branch. So both of those currents were split from here. That's the total current. It splits, flows across these two resistors, and then, of course, over here it merges again into the total current. So the total current that flows here will just be